All right, as you get into gas law problems, there's a lot of ways to approach it, and it really does not have to be as complicated as it usually appears. Okay, you basically have two major types of gas law problems. Okay, either the conditions are changing, which means your temperature's going up, or your volume's going down, or your pressure's going up. Something is adjusting. At least one factor is adjusting. At least one of those measurements is going up or down. Or you have a case where nothing is changing, and all we're trying to do is analyze how much of it there is or what one missing measurement might be. So the first thing you have to ask yourself is, are things changing or are they staying the same? And what I'm going to show you right now is a way to approach any problem where conditions are changing. Any condition at all, maybe multiple conditions, maybe just one thing. Okay? But usually in these gas law problems, you'll notice that as one thing changes, something else changes in order to sort of kind of level things out. Okay? They all have an effect on each other, basically. Now, what you have right here is called the combined gas law. Okay? And I don't know if you've ever seen it in this form, but basically what it does is it takes just what it says. It takes Boyle's law, and Charles' law, and all those other concepts and combines it into one formula. And you can use this for everything. Anytime conditions are changing, you can use this. Now, what's nice about this formula is it can convert into all those other little mini formulas, I say, like Boyle's law or Charles' law. It can convert into that whenever it needs to. Here's what I mean. Let's say you had a problem that said, oh, as the pressure goes up in this, what happens to the volume? And during the process, it says the temperature remains constant. So what if we don't have a temperature that's changing? Well, that's pretty easy. Here's what I do. If the temperature doesn't change, I just pretend the temperature isn't even there, and I have P1 V1 equals P2 V2, which is also known as Boyle's law. Okay, all I did was basically cover up the measurement that's not changing. And I can use this to plug in some values, plug in something for V2, plug in something for P2, plug in something for V1, and I can rearrange it using a little algebra to solve for whatever's missing. Okay, that's a pretty common thing to do. Well, what if, let's go back to the original formula, and I'll erase all this stuff up and show you another option. What if, let's T1, T2, you get a problem that basically says, oh, we don't give you any information at all about pressure. Or we give you some sort of scenario where the pressure has to remain the same all the time. If pressure has to remain the same, well, then I just eliminate pressure from this formula, and I end up with V1 over T1 equals V2 over T2, and I've got Charles' law. Okay? And I just treat it that way. And so I plug in the things I know, and there's going to be one thing like, I don't know, temperature 2 that I have to solve for, and I can cross multiply to make that happen. Okay, so that's another option. Now, sometimes you get a fairly complicated problem that has a lot of stuff in it. And what you'll notice is, a lot of times, if it's not specifically set up to avoid this, everything changes. That's why this is a very useful formula. If you have a certain scenario that has allowed for all these measurements to fluctuate, well, then they're all going to have an effect on each other. And so if everything were to fluctuate, well, you just plug in everything you know, and you try to solve for what you don't know. Now, sometimes that sounds a little easier than it really is. So let's look at what would happen. Let's say we plugged everything in, and what we were trying to figure out was T2. Well, the easiest way to approach this would be cross multiply. P1 V1 T2 equals P2 V2 T1. And all I have to do now is get T2 by itself, so I'm just going to divide by P1 V1, P1 V1, and if that's what I was looking for, here's the formula that would tell me that. Okay? So I'm using a little algebra to rearrange it. So this is a very versatile formula. Now there's a couple of restrictions we got to know here before I'm done that you're going to have to adjust for. Okay. Something you need to know if you're going to use this formula, and the same is true for Boyle's law and Charles' law and all those things, but especially this one, when you're using it, you got to make sure that all units match. Oops, bad spelling, match. And what I mean by that is if pressure right here is in atmospheres, then this pressure better be in atmospheres. So you might have to do some conversions. If volume is in liters, then it better be in liters on both sides. And the other thing we have to make sure is temperature has to be in Kelvin, okay, so that we avoid negative temperatures. Okay, we have numbers that will match up and mathematically work out. So these are the basic rules. All units have to match each other on both sides. Temperature's got to be in Kelvin. And if you have that, this combined gas law will get you just about anything you need if you have changing conditions in a problem.